Welcome to lecture 21. This is our topic. We are going to continue the discussion on the bipolar junction transistor. The acronym is the BJT. I think we introduced this last time. And last time we looked at trying to understand the behavior of the BJT in terms of a small equivalent circuit comprising a diode and a resistor, and then try to, from there, look at the IV characteristics of the BJT itself. And I left you guys with an example that I hope some of you have had time to look at. What I'd like to do today is to get a little more in depth into the current voltage characteristics of the transistor, and hopefully that will partially also serve as a review. And then do a few more examples, including the one that we talked about briefly at the end of last time. Okay? Anything you guys would like to discuss before I start? Okay. So this is our topic, the bipolar junction transistor. And by way of review, this is what an NPN BJT looks like. And once we feel comfortable with this, we'll also talk about the other BJT, which is the PNP. But an NPN transistor, an NPN BJT, looks like this. It's a semiconducting material, and it has 3 segments that are essentially, they are what you call doped with some impurities that give them some that induce some differences in their electronic properties. Again, we have not discussed the physics, so this is really just to present the terminology here. But this is what an NPN transistor looks like. It has 2 junctions between N and P on one side and P and N on the other side. And this is literally your base contact, your emitter contact, and your collector contact. Now, what we are concerned with at this point is not what's going on inside this device and what N and P mean. If they don't mean anything to you, which they likely won't, don't worry at all. Again, I'm just introducing the terminology. But what we do care about at this point is the circuit level behavior of the device. And for that, we have this symbol. It's a 3-terminal device. Base, emitter, and collector. And this arrow between base and emitter suggests that this is a diode. And normally, the way you operate the transistor, this diode is forward biased. In fact, there is also a diode between base and collector. But during the desired active mode, that diode is reverse biased. And you have these 3 terminals. So to fully describe the voltages in this device, you need 2 voltages, right, between 3 nodes. If I give you the base emitter voltage and the base collector voltage, you can, by KVL, come up with the collector emitter voltage, right? So you need at least 2 voltages. And that 2 voltages will completely define things here. And of course, there are 3 connections, so you need 3 currents. You have the base current, the collector current, and the emitter current. By the way, the reason we have indicated the directions like this is that during the active operation of the device, in the active mode, this is the direction of the currents. So these would be positive values. If you wanted to define them in another way, then you would have some negative values in active operation. So this is a very convenient convention. So what I'd like to do now is just to review the characteristics. And what we are particularly interested in is the collector current. Because very often the way this device is used, you have some input applied between base and emitter, one way or the other, and it's the collector current on the other side that you're using. And so it's very convenient to think of this as having an input on the left-hand side and an output on the right-hand side. And to analyze how things work, we want to see the behavior of the collector current as a function of the voltages for this device. Now, if you were looking at a resistor, you had just one voltage and one current. You had simple IV characteristics. It was just a straight line Ohm's law. For a capacitor, similarly, you had just one voltage and one current. For a diode, the same thing. For a BJT, you have 3 currents and 2 voltages. And in fact, the 3 currents also are related by KCL, as we said last time. So if you specify 2 of them, the third one would also be known, because IC plus IB going in should equal IE going out. Okay, so you really need to talk about 2 currents and 2 voltages. But most often, it's the behavior of IC, the collector current, as a function of VBE and VCE, which is of interest. And this is what we started to look at last time. You can formally think of, in fact, 3 regions of operation for this device. We talked about active and saturation modes, and we'll repeat them in a moment. But there's also this thing called cutoff, when it's off, and it's not doing anything. So it's not very exciting. And that's when your base emitter voltage is so low that that diode is not even on. So there is no current going there. Okay? So let's write these down. Regions or modes of operation. The easiest way to get into this is to also indicate a couple of voltage sources. Imagine I have applied this voltage between base and emitter, so I call this VBE. I have this base current here, and I have this emitter current here. And I have this collector current here. As I said, we need to also clearly define another voltage here to have all the parameters. So let's call this VCE, the voltage between the collector and the emitter. Or you could have another voltage source between collector and base. VCE would be the sum of VCB plus VBE. Doesn't matter. I'm particularly interested in the behavior of IC versus VBE and VCE. And this is what we briefly talked about last time. Oh, let's put it this way, and then I'll draw things. The 3 modes of operation, one is cutoff, and that's when nothing is happening. There's no current. And that's when this VBE is too small so that the base emitter diode is essentially off. It's not in its forward mode anymore. So for a real device, this would be a little bit less than 0.7 volts, maybe 0.4, 0.3 volts, and anything below. So essentially, when the base emitter junction is reverse biased. So the BE diode is off, and actually the CB diode, if you look at this, and you have, that's not an entirely symmetric structure, by the way you make it, but schematically. So there's a junction or a diode between B and E. There's another one between B and C. So in reverse, these are both off, or reverse is a better. better terminology. So that's typically when you have a VBE voltage here, or what I have applied here, that's either negative or slightly positive, but not quite enough to turn that diode on. So it hasn't made it to 0.7 yet. And similarly, the voltage between base and collector is also such that that diode is also reverse. What happens is when you keep increasing VBE, when this diode turns on, when VBE reaches around 0.7 volts, you start the active mode. So you enter the active mode. It's implied, yes. So the question is, why don't we have an arrow showing the other diode? Because in the active mode, what I was going to try to write, the other diode is actually reverse. Okay. So, and maybe you don't want to explicitly show a diode that has a reverse current. That would create a dissonance in people's mind. But yeah, so there is a diode there, but it's reverse. And again, once we talk about the physics of operation, hopefully it will make sense. How can it be that a reverse diode is letting current through? But it's really because these are not two separate diodes. It's one device. Two back-to-back diodes is not a complete picture, but this is a way to refer to it. The question is, we modeled the BJT. We didn't put a diode between base and collector. That was a model for the BJT, right? It was not the physics of the device. It was a model to represent how it behaves in a circuit. When I say a diode, I'm referring to the physical structure, what is there. Okay? Active, the BE. In fact, maybe to reduce this conflict, instead of calling it a diode, I'll call it a junction. How about that? Okay? But remember that each of these junctions are like a diode. So let's call these a junction because it's a junction between two materials. In the active mode, the BE junction is on, and this is what we saw last time, is forward or on. The BC junction is still reverse. And that's the counterintuitive part, which one can appreciate only once one studies the physics. And what we saw in an example was that, and we talked about, was that if you keep pushing things to make the other junction also forward, then you reach the saturation. The BE junction is forward. The BC junction is also forward. Now, part of the reason I'm writing this for you is for completeness. If you have difficulty with imagining what's happening there, what I mean by these junctions being forward and reverse, for now, don't worry about this. Okay, just write it down as a reference point for the future. Don't worry about what it means exactly. What really matters is the characteristics on the graph, and that's what I'm going to draw now. All right, this is what really matters. That the collector current, remember we said it can be thought of as the current of that base emitter diode. So it has this kind of exponential diode-like behavior with voltage VBE. So you would call this some saturation current times exponential of VBE by that thermal voltage, which is about 26 millivolts at room temperature. So there clearly you see that by increasing VBE, and this would be your typical 0.7 volts here. By increasing VBE around 0.7 volts, you would, in the active mode, you would increase the collector current. The other behavior that is of importance, which we talked about, was IC as a function of VCE. It's the collector current as a function of this VCE. And here's where I'd like to invoke that model that I showed you last time, where we had essentially a current source in the collector branch. And ideally, a current source, you wanted to provide a constant current. Now, that was a controlled current source, so it was being controlled by some other voltage somewhere else. But its own voltage, so the voltage applied to the collector, should not, to first order, affect the current of that current source. And that's why we saw that the characteristics looked essentially flat for a range of things. And then eventually, if your VCE became very small, eventually you reach the point when things turned off. And we call this region saturation. Now, what I'd like to do now is to make this one step more sophisticated and be more realistic. The characteristics are not, as you would expect, are not entirely flat. There is a small slope. So as you increase VCE, even in the active mode, the desired mode of operation, the collector current goes up ever so slowly. Okay, it's not perfectly flat. Flat would be ideal, but it's not. And then you have the saturation here. And like we said, this saturation starts at around 0.3 volts of collector-emitter voltage. Now, this was for a given VBE. And this is the region of interest. This is the region of interest. This is the active mode. Okay? If I use another VBE in the active mode, so if I increase VBE, the collector current will also go up. Okay, like this. Okay, let's draw this again. I'll use the opportunity to give myself a little more room here. So this is where the important stuff starts. Ideally, we would want a saturation, an active mode that's flat like that. So it's like a current source. You have a constant current for any applied voltage. In practice, like I said, it's not ideal, so it's more like this. And I'm exaggerating a bit. This slope might not be that high. Okay? In fact, I'll exaggerate it a bit more to be able to show something here. So this is really exaggerated, okay? But you can extrapolate this, and you will see that it will hit this axis somewhere. But below this 0.3 volts or so, you enter saturation. Okay? So let me write this down. Here is the active mode. And here is saturation. Now, this is for a given VBE. Let's call it for VBE1, for instance. If I increase VBE to VBE2, it will be like this. And again, this is an exaggerated view to show the slope. and it will hit the same point. Okay, and you can keep increasing VBE. So this is the direction of increase of VBE. It's not an ideal current source. It's a current source whose current is, to some degree, you might say, almost constant with the voltage, but not quite. And now, if I wanted to represent a current source whose current is not, or if I wanted to model the circuit, rather than an ideal current source to represent that mode, what should I do? Is there something else I could include to capture the fact that there is a slope there? That slope is telling me that by increasing VCE, IC is, even in the active mode, is not constant. It's increasing slowly. How should I capture that? Consider a current source, controlled or uncontrolled. This current here does not depend on the voltage across that source, right? What if I wanted to represent an element whose current is mostly this, but still does vary a little bit by increasing that voltage? So the current is not just that, but that plus a part that does increase with the voltage applied between these 2 points. What is an element whose current increases linearly with a straight line based on applied voltage? It's resistor, right? So you can model that effect by putting a resistor in parallel with a current source. This would have characteristics like that. And that is something that you do sometimes if that slope is of importance. Okay? And this is often referred to as some value VA, and it's called the early voltage. This is named after someone. And the early effect, again named after this person, is the fact that IC, even in active mode, is not constant with VCE. Okay, this is not something that would have a qualitative effect on many of the things that we see. I wanted to put it out there so that we know about it, but for a great many problems, we will neglect that effect and assume that that's a flat line. So we assume that this VA is basically a very, very large value, so that that's almost a flat line. VA is typically something between 10 and 100 volts, you might say. Okay, it's a large voltage on that side. The above view, or the above graph, is somewhat exaggerated in terms of slope in the active mode to show the early effect. As an approximation, very often we'll assume that the characteristics are flat in the active mode. A horizontal line. Let's remember the KVL and KCL also. So KVL is simply telling us that VCE is VCB plus VBE, and KCL is telling us that IE is IC plus IB. Okay. We also saw that we defined things, a couple of parameters, IC as being beta times IB and IC being as alpha times IE. For a good transistor in the active mode, or BJT, in the active mode, beta could be 50, 200, even 1,000. Typically, you might say ballpark 100. So let's say beta is 100. And how much is alpha? It's approximately 1. So let's say about 0.99. Okay. So if you look at your case CL, you can look at it like this. IE is, which is, yeah, so IE is IC, which is alpha IE plus IB. And you see equivalently that IB is 1 minus alpha IE. So it's a very small fraction of IE and IC. Okay. So the essence of the operation of this device is that you have at the input a small voltage here around 0.7 volts that turns on this diode. The current that goes into the device from the left-hand side is a small current, and you have something like 100 times the amount of that current going down the collector and the emitter. And of course, the collector and emitter are slightly different. The difference is the small current in the base. All right, enough of this. Let's go back to our example. And we started by looking at this circuit. Put an input voltage here, and we were interested at the voltage at this output node with this. Okay, we analyzed this briefly, and or not so briefly, and we realized that the big change in the output would happen when Vin is somewhere around 0.7. So when it goes from 0.5 to 0.6 to 0.7, gradually this input diode is turning on, and there is a large current in the collector that will then go through that resistor also and lead to a voltage drop at this node. And up here you had some voltage, constant voltage. Okay. But the next example that I ask you to think about on your own, which now I'd like to spend some time on, was this. I also added a resistor here. We are still interested in this V out. Let's call this R sub C and R sub E. A resistor in the collector and a resistor in the emitter. What I'm interested in is to plot V out as a function of V in. Now here maybe I'll start with a question for you guys. Let's do a clicker question. Is this device, this transistor here, in the active mode or in the saturation mode? The answer is we don't know. It depends. So let's try to analyze this device. Okay? Spend a few minutes on it. calculate and plot V out as a function of V in. And assume that VCC is a large positive number. What we are interested in is to see, for a given value of V in, arbitrary value of V in, what is V out? And so let's look at some test examples, test cases. Let's start with V in being 0. That's always an interesting point. So if V in is 0, what is V out? If V in is 0, what is V out? Well, to find out V out, things are easy because we have the collector current here, which also goes there. This V out is not connected anywhere else, so that's the same current. V out is simply VCC minus RCIC. So all I need to be able to determine V out is IC. Now, if V in equals 0, what is IC? I also have two other currents to be considered, IB and IE. What formulas should I use to analyze this circuit?
You have to imagine the diode.
To what?
You have to imagine the diode between the base and the emitter.
Yeah, so we have this diode here. Just imagine.
0.7 of voltage to start really running.
Yeah.
The current.
Yeah.
So until there, we won't be having much current going through the diode.
Right, that's correct. So let's try to write this down mathematically now. What is a rule, a law that I should be using to be able to bring some analytics to this? KVL and KCL. We don't have anything else, so that's always the answer. Okay. Well, what is KVL? Let's look at V in equals 0. What does KVL tell me? KVL says minus V in plus VBE, the base emitter. Remember, this is the base, and this is the emitter, and this is the collector. Plus VBE, plus the voltage drop across that resistor, is 0, right? If V in is 0, then VBE plus REIE are 0. What can I conclude from that? Well, specifically from here, I can conclude that IE is 0. Why is that? Why can I conclude from here that both VBE and IE are 0? Yes, but why can I not have a negative VBE and a positive IE? VBE is not grounded. VB is grounded, right? But VE could be something else. Why can I not have a positive VBE and a negative IE, or vice versa? So why am I able to make the conclusion that these are both 0? Intuitively, I think many of us feel that that's the case, but I want mathematical rigor in it. Well, imagine you have a positive IE, okay, which requires a negative VBE from this equation, right? But a negative VBE means that that diode is reverse. That contradicts a positive current going through it, okay? So that's something I want you guys to pay attention to. In this particular problem, maybe that's a small trivial thing, but this will become important in other problems. The reason I can make this conclusion is that a positive VBE here cannot live with a negative IE and vice versa, because the diode will allow current only in that direction once on. Oh, okay, so if VB is 0, you also go back here. You see that IC is also 0 because you're at the origin here. So V out, which is equal to VCC minus RCIC, is simply VCC. What if V in was 0.5 volts? What then? I still have the same equation. So minus V in plus VBE plus REIE equals 0. If this is 0.5 volts, what then? If Vn is 0.5 volts, what is VBE and what is REIE? Which one is 0.5? That's correct. The sum of the two, VBE plus REIE, is 0.5. But what is VBE and what is IE? IE is 0 and VBE is 0.5. Or you might say, in reality, IE is an extremely small number, but VBE is almost 0.5. And why is that? Because because 0.5 volts on that VBE is not enough to turn that diode on to any substantial degree. It's just starting to feel like it should turn on. It will allow a very, very small current, but we said approximately 0. It's very small. Okay, so IC is also a very small current, almost the same as IE, and that's approximately 0. And so V out is still more or less VCC. Not quite, but almost. And this keeps continuing until V in reaches 0.7 volts. Now, if V in becomes more than, more or less 0.7 volts, then what happens? You see, as you're increasing V in up there, it keeps going up until it reaches around 0.7 volts, and that BE diode turns on. And that's the moment when the current IE starts to go up. It becomes substantial. And then, as you keep increasing V in further, let's say now you increase it to 0.8 volts, 1 volt, 2 volts, 10 volts. Then what happens? How much will the current, the voltage across that diode change? Not very much. That diode will keep taking about 0.7, maybe 0.75. You push it maybe 0.78 volts. So as you keep increasing V in beyond that 0.7, the additional chunk of V in drops across RE. Okay? For V in greater than 0.7, you might say, again, going back to that same equation, minus V in plus VBE plus REIE is 0. Now this has become maybe 10 volts, whatever you have. And from here now you can do something interesting, because VBE will be somewhere around 0.7. So from here now you can calculate IE as Vin minus 0.7. Now this is approximate divided by RE. Because you see, as you keep increasing Vin more, that additional increase will drop across this resistor and gives you a current like that. If my diode was really that very simplified diode model where it had a fixed 0.7 volts, this would be a completely accurate equation. But of course, the diode is not a fixed 0.7. As you keep increasing Vin, this 0.7 also increases a little bit, but by a small amount. Well, what can I say for the output voltage, Vout? VCC minus RCIC, which is VCC minus RC, and IC is some alpha, which is almost 1 times IE. So this is VCC minus, now I'll just simply replace. Everything is constant except a linear dependence on Vin. Maybe it's better to bring the constants all next to each other. You can lump them like this. This is your Vout. So a linear function of Vin, decreasing function of Vin. Let's plot this then. Vout as a function of Vin. Started as VCC until Vin reached somewhere around 0.7 volts. And before that, at some point, you would start feeling this gradually. By the time that's 0.7, that has more or less turned on. And you see that if you put Vin equal 0.7, that equation will just still give you VCC within this approximation. And beyond that, then, you have a linear decrease. So this is the output versus input, right? Correct? Should we move on to the next example? All right, everyone happy with this? Correct? This is wrong. Let's take a break, and you guys will tell me why it's wrong after the break. It's not entirely wrong. Should we start, guys? So what's wrong with this? Continuing the same example. I claim that this was wrong. What is wrong with this? And why? Well, let's see. Let's take a point here. Consider this point. What is the value of VCE at this point? What is VCE? VCE is the voltage difference between collector and emitter. That's V out minus the emitter voltage, right? Now, the emitter voltage is V in minus about 0.7 volts. What is VC? Is that a positive value? Is it a negative value at that point? Is VC positive or negative? If my output voltage is negative, is VCE positive or negative? VCE is also negative because V in is a great positive value. VE is only 0.7 below V in, right? So V in is VE is a positive value. VCE is quite negative at this point. Around here. Because remember, VCE is V out minus VE, which is simply V out, or approximately V out minus V in minus 0.7 volts. Now, if V out is negative and V in is positive, this is going to be a negative value. So what's wrong with that? What's wrong with VC being a negative value? You're somewhere around here. You have long abandoned the active mode. You see, that mode of operation where your collector current could be said to be more or less equal to the emitter current, or alpha times emitter current, with alpha being somewhere near 1. You have long since abandoned it. The device is deep in saturation. So the assumption that IC equal alpha IE, with alpha being approximately 1, is not valid anymore. That is not valid anymore. So if this cannot go on like this, where should I stop it? It can't be that this whole thing is wrong. I mean, part of this curve has to be right. That equation for V out that I derived up there, which represents this curve, that should be initially correct, but it just can't keep going on until infinity like this. So it has to start deviating from this and start to kind of saturate somewhere. Where is that? How can I come up with that point? How do I find that out? Is my condition for saturation VCE equals 0? 0.3 volts. I mean, 0 is not too bad an approximation, but 0.3 is the ballpark. So all I have to do is to say this will keep going until VCE reaches around 0.3 volts. That's all. And beyond that, the device will saturate. So instead of all of this, we'll plot that line. But this continues until VCE, because as the output goes down, VCE is going down. Remember, the output voltage is simply the collector voltage. So as the output is going down with an increase in the input, VCE is going down. And this continues until VCE reaches around 0.3 volts. Beyond that, the device enters saturation. Okay? So all you have to do is to set that the VCE equal to 0.3 volts. Let's see if we can find that point out. VCE is VC minus VE. And VC is the same as V out, is what we have up there. So I'll just replace VCC plus this that's your V out minus a VE, which is V in minus approximately 0.7 volts. Okay? If you set VCE equal to 0.3, that will give you the V in value at which saturation starts. That will be somewhere, let's say here. So this curve continues like this. Let's call this V in of saturation. In this part, the device is in the active mode. Before that, you're in the cutoff mode. And then you're in saturation. Okay, so this is something that you have to be careful with, that in any transistor problem, you have to, for different values of input, different ranges of parameters, you have to consider whether you are in active or cutoff or saturation. And as you can see, that depends on the parameters of the problem. So in this case, for instance, VC equal 0.3, well, depending on RC and RE and alpha, you will get a value of V in that represents the onset of saturation in this case. But now I have a question about what happens in the active mode. Question about the active mode. If in the active mode, for a value of Vn for which the device is in the active mode. I change Vn by a small amount. Delta Vn. What is this? Can you do this on your own? Suppose I am operating in the active mode in this part of the graph. I have some Vn that keeps me in this region. And I change that Vn by a small amount, delta Vn. I'm interested in the amount of change in the output and the ratio of those two changes. Does anyone have the answer? That's right, with a negative sign. Times alpha, which is almost 1, right? Because look, call this equation 1. If you're in the active mode, that's the relationship, right? If you take dV out by dV in, which is really what that thing is, small deltas and the ratio of them. If you look at that equation, it's minus alpha RC over RE. And alpha being almost 1 is almost minus RC over RE. It's an inverting amplifier. For example, if you put numbers to this, and this could be a real example, a real scenario, you can say RC being 10 kilo ohms, RE being 1 kilo ohm. You have a gain, a voltage gain, or a differential voltage gain of approximately minus 10. Which means if you are in that active mode and if you increase your input by, say, 10 millivolts, your output will change by 100 millivolts. And if you're increasing the input, the output will decrease because the gain is negative. Now, this formula is not complete because an assumption has gone to this. And the assumption was that once you have reached the active mode, the input voltage stays fixed at the base emitter voltage stays fixed at 0.7 volts, right? I made that simplification. I said once your input has surpassed 0.7 volts, beyond that you have a constant 0.7 volt on the base emitter part, and any increase in the input will appear on this RE. That's not entirely accurate, of course, because as you keep increasing the input, well, the voltage across this diode will go from 0.7 to 0.71, 0.72. It will not stay fixed at 0.7, okay? Let's just remember that assumption. if you try to do a more realistic scenario, then you would factor in a little bit of change in the diode voltage as you increase the input. And that would lead to a modification to this formula. But this captures the essence of operation. And this is maybe the first place where you are seeing great similarity between something that this transistor is doing compared to something that we saw with op amps before. You are determining the gain, the voltage gain of this circuit, a change in the output over a change in the input, that is more or less determined by the resistors you have used in the circuit, rather than directly by the properties of the transistor itself. It's somewhat insensitive to the transistor. Not entirely. Again, this is based on this assumption. But it captures the essence. I want to do another example that's a little different to show another type of application. By the way, to make a connection, this is of the subcategory of the circuits that you would call a common-emitter amplifier. You have an input that's between the base and essentially the emitter side, and an output between the collector and the emitter. So this is just so that you have heard that name. Let's do another example. Let's do something numerical now, this time. Let's assume this is 10 volts. And this is 9.3 kilo ohms. The two transistors are identical. Beta is 100 for both of them. What is I? The current I is what I'm interested in. Approximate answer would be fine. Let's do a KVL here. Let's see what we get from that. Call this V1. Well, or let's define the node voltages. This is one node, right? All of this is one node. Let's call that VB. That voltage there. If the transistors are on, what is VB? Assume both devices are active. What would VB be? No, VB, the voltage at this node. Just look at the circuit. if the transistors are active, what is the drop on the base emitter part? 0.7 volts. So what is VB? .7 volts. What is this current? Let's call this I1. What is I1? How much is that? I was hoping that that 9.3 would give away the answer. Okay. That current is approximately 1 milliamp, give or take. Of course, if VB was instead of 0.7, if it was 0.72, okay, it would be slightly different. But give or take, 1 milliamp. Now that current I, if I try to focus in on here, to give myself more room, that current I is a sum of this collector current. Let's call this IC1. And then IB1 and IB2. Right? That current I1 is IC1 plus this, which is IB1 plus IB2 by KCL. Okay? Which is IC1 plus IC1 over beta plus IC2 over beta. Now, if you look at this device, at this configuration, what would you guys say the relationship is between IC1 and IC2? Equal, because they have the same VBE. If I go way back to the beginning, remember IC was an exponential function of VBE. If the two transistors are identical and they have the same, their base is connected to the same point and their emitter is both ground, so you have the same VBE for both transistors, they will both have the same current. The two transistors are identical and also have the same VBE. So their IC will also be equal. So I can then write I1 is IC1 plus IC1 over beta plus IC1 over beta. And beta is 100, so this is IC1 plus 2 IC1 over 100. Now, if you don't want to be very picky, you could say, well, this is approximately IC1, because it's 1.02 IC1. So this is exactly 1.02 IC1, or approximately IC1. So if I1 is 1 milliamp, as we found out before, so is IC1. Which means so is IC2. And I is just IC2. It's the same current there. Now, you might make an interesting observation. The value of I did not depend on that 1 kilo ohm resistor. What happened? Why is that? What was it in the circuit that made the value of I not depend on the 1 kilo ohm resistor up there? It was this. Look at where we got that current. The way we calculated it was through the transistor current. And the transistor is acting as a current source. Like we said from the beginning when we started this discussion. Remember that model of the diode and the controlled current source on top of it? That's what this is doing. The transistor is acting as a current source whose value, whose current, is determined by what you feed it to its input. Now you could have fed a given value of VBE at the input, a very precisely calculated base emitter voltage, so that when you take the exponential of VBE over VT and multiply by IS, you get 1 milliamp there. But I think you would agree with me that that would not be a good design because that would be extremely sensitive to the precise VBE input. Whereas this circuit, what it has done is taken another transistor with same properties, same beta and everything, connected its base and collector, and put it in series with this 9.3 kilo ohm resistor. Now, the left branch here has essentially determined the current I1 because you know that approximately 0.7 drops across this transistor. The rest is left for this 9.3 kilo ohm resistor. Now, whatever this current is, the other transistor, which sees the same exact VBE, has mirrored in its own collector branch. This is actually called a current mirror, and it is a basic design for a current source. So far, we've talked about voltage sources, how you actually make a real voltage source. We talked about that, DC voltage sources, using diodes and all that. This is a current source. How would things change if I change the 1 kilo ohm resistor to 2 kilo ohms? Nothing. Regardless of the voltage variations in this collector branch of the second transistor, the current in this would not change. So you have something that you can connect different values of resistors to, and it would drive the same current through them. And that current is determined by the other side of the circuit. What if the value of that resistor, if I swapped it with a 10 kilo ohm resistor instead of 1 kilo ohm, then what would happen? What if it was 20 kilo ohms? Exercise for home. These are 4 little exercises that directly build up on this. Okay, please try this at home. But remember, so there are two very important things that we saw today in terms of applications of transistors. These are very of broad importance. This differential gain that we saw in this common-emitter amplifier, and this current mirror configuration acting as a current source. But really, it would be very hard to understand these without, again, going through these basic IV characteristics, thinking about the different modes. Again, remember that for many of the things we do, we are not concerned with this increasing slope in the active, or that non-zero slope in the active mode. Very often, we assume that they are flat. Here, I wanted to show this early effect to you so that you're aware of it. Okay? Please review these and do this little exercise at home. And we'll continue next time. Thank you.